Hello everyone, my name is Shubham Kartwal and I'm a final year PhD student at the University of Michigan. It's my pleasure to welcome you to my talk. Our work is titled HetSim, Simulating Large-Scale Heterogeneous Systems using a Trace-Driven Synchronization and Dependency-Aware Framework. I would like to begin by thanking my colleagues from the University of Michigan and the University of Edinburgh for their effort. Let's jump right into it. As we all are quite familiar with, the end of Dennard scaling and slowdown of Moore's law have spurred the growth of heterogeneous architectures that are composed of different kinds of computing units. The example on the top shows a heterogeneous SoC that employs a few out-of-order cores, some in-order cores, fixed function accelerators, and a coarse-grained reconfigurable architecture that's in itself comprised of many small processing elements or PEs. Further, the rise in heterogeneity has been accompanied by improvements in compute that have outpaced the growth of memory bandwidth. This has naturally led to more applications becoming more and more memory bounded as technology has progressed, as we can see in the figure. While there is a significant trade-off between the resources required and the accuracy at different stages in the design process, trace-driven architectural simulation has been widely adopted for early-stage design space exploration. In a nutshell, trace-driven techniques generate memory and compute accesses offline and feed them into a model of the target hardware. Trace-driven approaches have gained popularity as they demonstrate good trade-offs between simulation speed and accuracy. However, prior trace-driven frameworks have demonstrated such approaches only in the context of chip multiprocessors or CMPs, and there hasn't been a solution proposed for large-scale heterogeneous systems, especially ones that scale up to thousands of cores. We further observe that the trace formats in prior work lack crucial information, such as tokens for PE-to-PE communication, memory dependency annotation, and the program counter tracking for prefetching support that limits them to simulating only a certain category of hardware. In this work, we aim to address these inefficiencies and provide a flexible trace-driven simulation environment through HetSim. To begin with, HetSim requires a detailed model of the target architecture and currently works with the popular Gem5 simulator. The target model should have a parallel PE system and a memory subsystem that interact with each other. HetSim also supports a standalone mode where the user doesn't require detailed PE models, and we'll discuss more on that later. A power model of the target is optionally required if the user desires power estimations. Next, a multi-threaded version of the target application is implemented using C or C++. This could be an example of a 2D convolution for a DNN accelerated target. The code is then modified to use HetSim primitives, as shown here, where we push data through a word queue instead of passing it through a software construct. In this context, we define primitives as hardware functionality that can be emulated in software, and examples of those could be word queue push operation, as is shown in the example here. HetSim is packaged with a set of common primitives, such as pushes or pops through buffers, synchronization signaling operations, and so on. And it supports extendability by the user, and we'll discuss more on that later. We provide the user with a template specification file that is modified to model the target. Some of the information contained in this file are the address space to which memory accesses are captured, the types of intermediate representation instructions to be captured, latencies of operations, and so on. The cycles parameter, for instance, in this case, can be increased to model a slower PE or decreased for a faster PE. Finally, HetSim requires a native multiprocessing system with sufficient resources for trace generation and replay. We note that the trace generation step is sped up with more threads and faster storage, whereas the trace replay step benefits from higher single-threaded performance and more memory on the native system. Once we have the inputs ready, the first step is to generate the compiler plugin based on the specification file. This is an automatic step and is run once per the target architecture. The model generation script takes the user specification file as input and processes it in two phases, namely the JSON parsing phase and the model-specific extraction phase. This step generates the compiler plugin that performs program analysis and code generation, and also the trace library itself that interacts with the instrumented binary and thus generates the traces into the trace files. This is a snippet of the specification file, and this is from the generation script. The green box shows a list of LLVM instructions that are filtered in, while the blue box shows the metadata recorded for each PE. Lastly, the red box here shows primitive specific information, and these boxes are parsed differently by different parts of the generator, as is shown. The next steps are responsible for compiler pass generation and creating the tracing library itself. The compiler pass CPP file is generated by the generator script. Here, the red box performs code generation to identify primitives in the user code. Based on the function signature, the identification part itself identifies the function name, and the instrumentation part iterates over the primitives. As we see in the instrumentation section, an if-else block is generated for each primitive, where it walks over the arguments to the function call and collects them into a vector. Different primitives may have different number of arguments, and this is automatically handled in the generate model script. The tracing library is emitted similarly, and it's shown on the right. The second step involves the actual compilation, during which an emulation library is used to generate two binaries for the software emulation. The uninstrumented binary is generated and run on the native system to verify functional correctness of the application. The instrumented binary is generated using the compiler pass plugin and the tracing library from the previous step. The instrumented functions include memory accesses, computation, and other operations that we classify here as implicit primitives, as well as hardware-specific functionality like the ones we discussed before, which we refer to here as explicit primitives. During trace generation, the compiler pass scans for uses of primitives in the trace specification and instruments these with tracing calls. The left snippet shows the application program invoking the pop primitive, and the right one shows the compiled IR. Here, popj is the actual call, and that is preceded by the tracing call, which is C worker pop. Similarly, %4 is an actual load instruction, and %3 is the tracing call that emits the load into the trace file. The API that emits these calls are exposed to the user for manual instrumentation if desired. The instrumented binary is executed on the native machine to generate the trace files. Following that, the detailed Gem5 model is modified, where the cores are swapped with the TREs that are responsible for replaying the traces through the model. This is done to generate the performance and power estimation. We note that a major source of speedup comes from approximating compute operations using stalls, whereas memory operations are reproduced with high fidelity, and this ties with the move towards accelerating memory-bound applications, as I had discussed previously. Example traces are shown in this figure for two PE types in a target architecture. Our trace format captures the key pieces that we identified previously to be missing from prior work. For example, P2P communication using the push bcast primitive shown here, program counter tracking by annotating loads and stores with virtual program counters, and finally, dependency tracking by maintaining a dependency list next to each token. In this specific example, this feature enables the PE to issue load at PC10 and 11 in a non-blocking way, since they do not have dependencies between each other. However, the stall in line 8 blocks until the two load responses return, because they are annotated as dependencies for the stall token. We now move on to discuss some use cases of HetSim and illustrate how to add support for custom primitives. The typical use case when starting with a new architecture model is shown here. The user implements their architecture in Gem5 and connects the TREs, modifies the specification for the target, generates the compiler plugin and tracing library. The user then implements the application using HetSim primitives, verifies the functionality of the application, generates traces by running the instrumented binary, and finally runs the traces through the TRE-enabled Gem5 model, and this gives the user the required statistics. HetSim additionally supports the following use cases: profiling a new application on the existing model, exploring different design points on that existing model, simulating after making modifications to the hardware model, exploring different design points with different PE types, and finally also modeling ISA extensions simply as primitives. These use cases are described in detail in the paper. HetSim also supports a standalone mode where the user altogether skips implementing detailed models of the PEs in the target and instead uses the TREs directly in their model with the remaining memory subsystem. This is useful at early stages of the design process when coarse performance and power estimations are desired with fast turnaround times. As I alluded to earlier, HetSim supports the addition of user-defined primitives, and here I'll show an example of a sleep primitive, where a PE calls a sleep function to go to sleep and is awakened by a different PE that calls wake. We first add a new function definition into the emulation library code where we implement sleep using a condition variable and also a mutex that is private to each PE. Here the CV is signaled to by a corresponding wake call initiated by a different PE. Next, we add an entry to the user specification JSON file. And finally, we implement the primitive in the Gem5 TRE class member function called tick, where I show a snippet of tick here. Here we use a simple trick where we have the TRE return without scheduling its next clock tick, and that is instead scheduled by a different TRE on its behalf. This approach avoids the expensive alternative of a polling mechanism that would have otherwise led to significantly increased simulation time. Finally, we move on to our evaluation. For this paper, we used HetSim to model two target architectures. The first one is called Transmuter, which is a highly reconfigurable architecture. It's a tiled design where each tile consists of one local control processor and multiple general purpose processing elements. The L1 and L2 levels in the architecture allow for reconfiguration of the on-chip memory and sharing type. We evaluated three workloads in this work, which are general dense matrix multiplication or GEM, dense matrix vector multiplication or GEMV, and finally sparse matrix multiplication or SPMM. These workloads show different characteristics in terms of arithmetic intensity and compute or memory boundedness, as we see from the table. GEM and GEMV are implemented further using a blocking approach, while SPMM is implemented using an outer product algorithm that splits the computation into a multiply and merge phase. We evaluate these on two transmitter configurations, one where L1 and L2 are both shared cache, and the other where they're both reconfigured into the private cache mode. The second target is an SPMM accelerating chip that uses three kinds of processing elements: a fixed function PE, an ARM Cortex M0 processor, and an ARM Cortex M4F processor. We focus on the first system in this work for demonstrating the efficacy of HetSim and use the second system for validation of HetSim against real silicon. Finally, we evaluate HetSim on a 32-core AMD Threadripper machine with 128 gigabytes of main memory. First, we'll show some scalability results using HetSim with the transmuter target. On the left is shown the wall clock time for trace generation with different transmitter sizes involving different number of cores, and also the trace replay time for the whole system. On the right are some bandwidth and throughput studies on the transmitter architecture that's enabled by HetSim. In fact, HetSim enabled us to simulate up to a 64 by 64 transmitter configuration that has a total of over 4,000 PEs, whereas our detailed model couldn't scale beyond an 8 by 16 design. Going back to the plot on the left, other than SPMM, we observed that the workloads have plateauing overhead of trace generation, and we suspect this is to be related to the bandwidth boundedness of the SPMM application on the native system. We observed the trace replay time to be increasing with increasing number of cores in the system. We also noted that trace generation is usually a one-time cost, such as for experiments involving sizing hardware structures, buses, sweeping clock speed, and cache sizes, and so on. And traces are only required to be regenerated only if there is a change that affects the instructions executed by a PE itself. We observed that the one-time cost of trace generation is 1/10 to 2.5x the time required for a single trace replay run, and it's usually amortized over multiple trace replay runs. We now study the important metrics of speedup and accuracy in comparison to a detailed Gem5 model. In summary, we get about 3.2 to 10.4x, averaging 5x speedup over the detailed model using HetSim. And this is at the cost of deviation in runtime and power, with the runtime deviating from 0.2 to 57% with an average of 15.1%, with the power deviating between 0.0 and 24.2, averaging 10.9%. Now we look at a set of graphs for each of the three evaluated workloads. The orange bar here represents simulated time of the target architecture, and the other two bars show power and L1 access count. The speedup is indicated by the line graph, And each column here represents a different transmitter configuration, so either the shared cache or private cache. And each row represents a different problem size. I discussed some key takeaways in this slide. For GEM, we see that the accuracy is improving with increasing matrix size, and the accuracy for private cache is better than shared cache. This is because shared cache incurs far fewer L1 misses, and thus the shared cache timing is entirely dependent on the accuracy of simulating the compute operations, which is what HetSim compromises on. For GEMV, the blocking versions are much more accurate, as we see here, because these versions have the GP synchronized with the local control processor after 16 or 32 elements of the vector are processed, and that leads to self-correction of errors. The power estimations in GEMV are fairly accurate with just a maximum deviation of 5.7% because the traces consist mainly of memory accesses, which are faithfully reproduced. For SPMM, there are two opposing trends. We see that the L1 access count deviation, it's overestimating the L1 accesses for private cache, and it's underestimating it for shared cache. While the HetSim version generates equal number of memory accesses in both hardware configurations, we observe that the detailed model generates far more traces in the shared cache case. This is due to dynamism in runtime variables such as scheduling and contention, which is not modeled in HetSim. Finally, we observe the speedups to be improving almost consistently with increasing matrix dimension, which is great for large graphs that are usually the inputs to sparse matrix multiplication kernels. Here we look at some design space exploration we performed using both HetSim and the detailed GEM5 model. And we note the accuracy of predicting the best configuration for different problem sizes. These plots show the performance with different problem size scaling for the 3 different workloads. The stars here show the best performing transmitter configuration as predicted by the detailed GEM5 model. The checks show cases where HetSim made the same prediction as the detailed model about the better transmitter configuration. For GEM, we see that HetSim has made accurate predictions for 7 out of 8 configurations, while it's achieved 100% accuracy in prediction for all the data points for the other 2 workloads. The key takeaway here is that for experiments that determine the value of a categorical dimension, such as the best mode of data sharing in this case, the absolute value of errors introduced in the timing estimations with HetSim are not very significant, and we can still predict which transmitter configuration in this case is best using HetSim with reasonable accuracy. In the final part of our evaluation, we look at the correlation between HetSim and the 40 nanometer SPMM acceleration chip. We sweep the bandwidth on the x-axis and look at the performance on the y-axis. The average error in estimated performance is 32% for the multiply phase and 16% for the merge phase. The higher error rate for multiply is not an artifact of HetSim, but it's due to the differences in main memory module between the GEM5 model and the actual chip. HetSim fundamentally trades off simulation performance for accuracy of simulated results. Here are some known sources of errors. HetSim doesn't model pipelining within a PE and assumes fixed latencies for instructions. Frequent synchronization and busy waiting generate additional memory traffic that is dynamic and cannot always be modeled accurately in HetSim. There are inaccuracies due to differences in emitted instructions if the native machine's ISA does not match that of the target. This was the case with transmitter where the native machine used x86, whereas the simulated PEs used ARM cores. A related impact is due to HetSim instrumenting at the LLVM IR level. HetSim provides the option of filtering out primitives in the specification file, and overfiltration can introduce inaccuracies, although it also benefits simulation time. For PEs that use instruction caches, HetSim ignores the effect of instruction fetch, and thus also the bandwidth impact due to sharing instruction streams of data and the latency impact of iCache misses. There is finally the power impact of instruction processing in the PE pipelines and accessing the SRAMs themselves that's being ignored. To conclude my talk, we developed a tool called HetSim to address the issue of large-scale simulations for heterogeneous systems. We introduced the notion of primitives and packaged common ones with the latest HetSim release. HetSim enables flexibility to support modern hardware mechanisms by embedding additional information in its traces. We demonstrated simulation time improvements of 3.2 to 10.4x over detailed Gem5 models, with just a deviation of 0.2 to 57% in terms of runtime and 0 to 24.2% for power. HetSim is freely accessible under the BSD3 license, and we encourage everybody to try it out. We also added a Jupyter Notebook link in this slide that we prepared to help the user get started with HetSim. We encourage user contributions to this repository, especially to grow our primitive library, and this will enable fast design space exploration of a wider set of hardware. This is a note from our sponsor, and I thank you for attending my talk.